Hi everyone. Here we present our work, Privacy Preserving Online AutoML for Domain-Specific Face Detection. Let's imagine a situation where we want to serve a platform to customers. What this platform does is that it produces good models automatically for any customer dataset given. One example of such a platform is what we show here, Microsoft Custom Vision. Building these platforms can be very challenging. As customers' datasets can be very diverse, it's unlikely that one single model or training recipe fits them all. So, we either need to hire some R&D forces working on the model tuning, day and night. Or else, we use the machine power. We can leverage the advances of AutoML techniques to search for hyperparameters or neural network architectures. The idea of AutoML is straightforward. It uses a solver, or optimizer, to mimic humans' behavior in performance tuning. However, AutoML is notorious for its high computational cost. Recent arts often require hundreds to thousands GPU hours to tune a moderate-sized model. For our platform, this will soon become a problem, because we need to burn those dollars for each dataset over and over again. But there is an opportunity. As you might notice, dataset 1 and dataset 3 in this figure looks alike, as they both contain faces with masks. Intuitively, the optimal configuration for these datasets should also be similar. If we can smartly identify those similarities, we'd be able to save the expense of searching from scratch for dataset 3. We note the constraints and challenges here. Firstly, we wish to identify which datasets are similar in terms of their preference of hyperparameter configurations. Only with this information, we would be able to effectively predict the best configuration for any upcoming dataset. Secondly, since this is an online platform, we have the opportunity to leverage the AutoML records from previous users to continuously improve the algorithm, so that the platform will continuously enhance itself, and customers coming later can start at a better point. Lastly, and most importantly, all the problems above have to be solved under the constraints of privacy. In other words, the raw face images should never be disclosed to the central service. Instead, the platform should merely collect the minimal amount of information about the dataset that is very much required to make recommendations about training configurations. We present the HyperFD framework. Instead of uploading the raw images to the server, each local client only uses a meta-feature extractor to get a dataset level representation and sends it to the server. Note that the meta-feature extractor here is retrieved from the server side, and it's tailored for a particular configuration space, for example, hyperparameter search space. Then, the platform uses a learnable performance ranker which contains another configuration encoder to generate a configuration encoding and selects the top optimal training configurations. Finally, the client obtains recommendation from the server and trains the face detector locally. The client can optionally share its testing performance, as well as an updated copy of MetaFeature Extractor to help the platform further improve its service. The process repeats to serve a number of customers. As time goes, the performance ranker on the platform gets more and more powerful as it's getting more feedback. Meanwhile, only dataset meta features and the testing performance has been transmitted upon networks, which effectively protects the training data privacy. We then list out the technical contributions of our framework. On one hand, we design a novel hierarchical feature extraction approach that starts from anchor level, followed by a series of aggregations to generate a high-level dataset feature. On the other hand, we reduce the rest of the problem into a privacy-preserving continual learning problem. The key challenge here is that the meta features stored on the server side are generated by a legacy version of MetaFeature Extractor, which has already been updated due to continual learning. Meanwhile, we have no access to the raw data due to the privacy constraints. To address those challenges, we design a novel meta-feature transformation module combined with 3 loss functions, which guarantees stable and effective learning of the platform. Extensive experiments demonstrate the power of our framework on both hyperparameter optimization and neural architecture search. We've also visualized the learning process in hope of a deeper understanding. One interesting thing we noticed is that the meta-feature space learned upon different configuration spaces are rather different. This justifies the necessity to optimize the whole framework in an end-to-end manner. Thanks for listening.